Hey guys, in this video we're going to talk about using substitution for certain trig integrals. Let's just get right into it. So the first one that we're going to do, we're going to evaluate the integral of tangent x dx. So to use substitution for this, so as it stands you really can't substitute anything, but what you do know about tangent is that you can rewrite this as the sine of x over the cosine of x. And so now from here you have a couple decisions to make. And I did actually cover this in depth in another video, but I'm just going to give the whole explanation again here in case you need to hear it. So when it comes to substitution, you always have some choices that you have to make, and there is usually like a best choice. So you might think to yourself, oh, I want to set my u equal to sine of x, and then my du would equal cosine of x dx. And you might think, oh, here's my cosine of x dx. The problem is that the way that this is written, this cosine of x is actually in the invisible numerator, right? All of this would technically be over an invisible negative or over an invisible 1. So because of this, this is actually not the situation that we have here, right? And when you have your du has to be set up so that like it has to exactly replace exactly how your problem is written. So this is not the situation that we have here. So this is kind of giving you an idea that this is not the way that you want to go with this. So just a note on troubleshooting. So if that doesn't work, then just by process of elimination here, what I want to do is I want to set my u equal to cosine of x, and then my du will be negative sine of x dx. And now this actually works because sine of x dx, that's this right here. So both of these things are in the numerator. So the only manipulation that I really have to make here then is I have to rewrite this as negative du equals sine of x dx. So now just take a look at kind of how this is all going to get replaced. So this part here will replace this part here, and this part here is going to be what I substitute in here. So just want to be nice and clear with that. Okay, so now if I make these substitutions, I really get, we'll call this negative 1 du over u. And so that I can evaluate easy peasy as long as you remember that this is the natural log of u. This is always one of the tricky ones. People always forget that when it's just this format, then it's just the natural log of u. Okay, so now what I have to do is I have to replace my u. Let me clear this stuff off. And so now I'll just rewrite this as the negative natural log of cosine of x plus c. And so now we're actually going to manipulate this a little bit. So because this is negative, so we can use what's known as the power rule. So I'll just state that real quick for you over here. So basically that says if I have, we'll say r times just any logarithm, I can rewrite this as this exponent. So this invisible negative 1 right here, I can actually rewrite this so that it goes kind of into the cosine, like this. So I can actually think of this as the natural log of the cosine of x, all of this to the negative 1, which then I can rewrite this as the natural log of 1 over the absolute value of cosine of x. And then what would that equal? So that would just be the natural log of secant x. And so that would actually be the final answer in this case. So just to summarize, this equals this. That's the shorthand of the rule there. Okay, so I've got that integral. Now let's pivot and let's take a look at secant x. So this actually will require a very clever manipulation. So as this is written, so if you just start thinking about this, so with secant x, so I know that secant x is equal to 1 over cosine of x, and it's not like in either one of these cases there's a good choice of u here, because when you take your du, you're going to get something that's not helpful to you. So this kind of tells you then that the first like manipulation that would probably come to mind isn't going to work. So this is kind of telling us then we're going to have to get a lot more creative. So the next part of this requires a little bit of creativity, and part of this part of calculus and like where calculus starts to go is this requires a very specific trick that you probably wouldn't know just off the top of your head. So if you're looking at this next part and you're like, oh, I would have never figured that out, like part of it's just practice and knowing how to kind of game these problems. So an observation that's still not going to totally help us, but what I would really like, I would like to have some sort of situation where if I were to say set my u equal to secant x, that I could get this desired du. So I'd like to figure out some way to kind of manipulate this so that maybe I could actually have a du that looks like this. So basically what you would do is you would then just start throwing things at this to figure out what can you multiply this by to make it work. And so just to also give you a little bit more insight into the reasoning here. So I'm not going to write the integral, I'm just going to kind of show you like ways to think through this. So multiplying this by different terms is kind of one way that you get creative with this and you start exploring. So I just throw something out here. What if I multiply the top and bottom of this by secant x? So I'm just doing this for the purpose of trying to figure out what my u might be. And I can see, as this is written, this is not the du that I want, right? So this could have been my u, but again, if I take the derivative of this, this is going to be secant squared x. That's not quite what I want. However, this kind of helps influence then maybe what I should be multiplying this by. So this secant squared x, this is the derivative of tangent. So why don't I extend, so I'll erase this, and I say this was a good guess, let's play around with this again. And then I say, well, what if I multiplied it by tangent? So this is still not right. I'm just kind of trying to give you a little insight into how one might play around with this. So look at what happens if I try to do this. It still isn't quite right? In fact, I've almost messed it up even more. Like now I have something that doesn't even make any sense. So I felt like tangent had something to do with this, but this is not quite it. So I swing again. This is very normal in the process of doing mathematics, of just sitting here and playing around with things. So then I say, okay, what about if I add tangent to this? Okay, so now what would I get? I get secant squared x plus secant x tangent x, all of this divided by secant x plus tangent x. And ooh, here we go, right? So now we've actually got what we want. So in playing around with this, I figured out the proper manipulation. So look at this. What is the derivative of secant x? It would be this part here, secant tangent. What is the derivative of tangent x? It would be secant squared. So this is actually the manipulation that we wanted. I just wanted to give you a little bit of insight into like, how does one even figure this out? So let me get rid of this. And now let's do this. So I'm going to take my secant x, and now I'm going to multiply it by exactly what we were just working on. So secant x plus tangent x over secant x plus tangent x. And now I'll go ahead and multiply it just like we did before. So I get secant squared x and secant x tangent x over secant x plus tangent x. And now we can go ahead and set our u. So my u now will be the denominator. So it'll be secant x plus tangent x. And then my du, so the derivative of secant x is secant x tangent x. And then the derivative of tangent is secant squared x. And so check that out. That is the entire top part of this, the whole numerator of this, right? So now I can rewrite all of this. So this is going to be rewritten as just du over u. Boom. And now I can go ahead and finish this. So this is the natural log of u, of the absolute value of u plus c. And now I just replace my u. So this will be the natural log of secant x plus tangent x plus c. And there you go. The integral of this, so if I'm trying to take the indefinite integral, it will be this. Boom. Okay, so now I have cotangent x and I have cosecant x, and these are almost identical kind of strategies. So instead of having now sine over cosine, this will be cosine of x over sine of x, and it's still the same idea though. So my u will be sine of x and my du will be cosine of x dx. And so then this will be the integral of 1 over u du, and so then I get the natural log of the absolute value of u plus c, and then this will be the natural log of sine of x plus c. So very similar flow to doing tangent. And then for cosecant, so it's also going to be very, very similar. So instead of multiplying like we did here, secant x plus tangent x, now we're going to flip it to cosecant x plus cotangent x. So I'll just go ahead and set this up. So I've got this times cosecant x plus cotangent x, and then this will be cosecant x plus cotangent x. So I'll multiply that all together. So I got cosecant squared x plus cosecant x cotangent x, and then blah, 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 all the stuff in the denominator, right? And so then your u will be the same kind of deal as last time. So my u is cosecant x plus cotangent x, and then my du. So this is the only thing that's a little bit tricky. So the derivative then of cosecant is negative cosecant x cotangent x. Let's see, I'm kind of running out of room here. Let me write all of this maybe under here. Du, so this is negative cosecant x cotangent x, and then the derivative of cotangent is negative cosecant squared x. So what that means then is my du will now have to have a negative in front of it. So I'm kind of running out of room here, so let's see, I'll write that down. Just so it'd be negative du equals cosecant x cotangent x plus cosecant squared x dx. So this is the replacement then that I'm going to make. So this will become 1 over u times negative du. And I've talked about in another video just like writing this out and then rearranging this. So this will really be negative 1 over u du. So this is the negative natural log of u plus c. And now I'm running out of room, so let me just clear off all of this so that I can finish it. All right. Okay. So now this will be the negative natural log of cosecant x plus cotangent x plus c. And in this case, like rewriting this doesn't really make any sense, so we just actually leave the integral like this, or the answer like this. So here you go, and there's my answer, and so we're good to go. So those are the 4 trig integrals that you can use substitution for in more creative ways, so hopefully that was helpful. If you're looking for a longer explanation of how to use substitution, or you're looking for more examples, I have plenty of videos on that, so hopefully I'll see you in some other videos.